Okay, here's a little circuit with a cap, and we're going to go back and forth between frequency and time domain and look at some of the weird math that happens. So we've got a 5 microfarad cap, we've got some current, we've got a voltage across this thing, and it's given that this voltage signal as a function of time is 30 cosine 4000 t plus 25 degrees, and that's in volts. And we want to find the capacitive reactance X sub C, the Z sub C, the capacitor's impedance. We want to find the phasor current, I phasor, and the time domain current, I of t. So for part A, we have this formula for the capacitive reactance. It's just minus 1 over omega c. So it's minus 1 over omega is 4,000, and c is 5. C, the capacitance here is, it's given. This is C equals 5 microfarads. 5 times 10 to the minus 6. So it's going to be minus 50 ohms. Okay. That's the capacitive reactance. Then the part B, the impedance, Z sub C, it's just J times that, J X sub C. So X sub C is a scalar. It's just 50, and Z sub C is a phasor. So we use this little arrow on top notation. So it's going to be just add the J in front, so minus 50 ohms, minus J 50 ohms. So this thing, if you looked at it as a phasor diagram in rectangular, it's X is 0, so there's no real component. There's just this imaginary component going straight down at 50. So minus is down at 50. This is, if you put this in full. So this is a rectangular phasor, which looks like this. If you put it in polar phasor, it would be this. Or, there's really a 0 in front of this. It's really like 0 minus J 50. Okay, so this is 0 minus J 50 is rectangular phasor. 50 angle minus 90 is polar phasor. This is the phasor diagram. Okay, so yeah, different ways to represent the same thing. So part C, we want to know what is the phasor current, I. So we're just going to use Ohm's law. So Ohm's law in the phasor domain is V equals, I phasor, Z phasor. Okay, so, so Z is... we're solving for I. So I is just V phasor over Z phasor. And it's going to be, so this guy here in phasor domain is going to be 3 with an angle of 25 degrees volts. So, or 30 with an angle of 25 degrees volts. So that's V phasor, 30 angle 25 degrees. Divide by Z phasor, which is 50 angle 90. It's 50 angle 90. Now your calculator should be able to punch these out, okay? And if you need to figure out how to make that happen, so just punching that into the calculator, it's 0.6 angle 115 degrees amps. That is I phasor. You need to get these done in your calculator. Now, if you want to just understand it a little bit better, we can play with the rectangular here, right? And so this guy would be 30. So at 30 angle 25, it looks like this in the phasor diagram. It's going to have a magnitude of 30 and an angle of 25. And if you work out the trig on this, it's going to be 12.7 on the y and 27.2 on the x. So in rectangular format, it's going to be okay. So this is V phasor. Is 30 angle 25 in polar phasor? It's 27.2 plus J 12.7 in rectangular phasor. So this 30 angle 25 is going to be 27.2 plus J 12.7 divided by this Z, which is, we could leave out the 0. It's really just minus J50. So here's where weird things happen. So it turns out that 1 over minus J is just J. And I'll leave this, you can prove this, but if you multiply the bottom and the top times J, J over J, and then expand the J's into square root of minus 1 and do some canceling, you'll see that this is true. So here the J's cancel, and you get minus 12.7 over 50 for these two terms. Now this term here, that you could bring the J to the top and make it plus, and you'll end up with J 27.2 over 50. Okay, and then that if you divide that out, you end up with minus 0.254 plus J 0.543, which is, if you do the phasors on that, it would be the x component would be negative 0.254, and the y component would be positive it would be over here. It'd be positive 0.543. So this get rid of that. This thing here would be, what's the angle on this thing? The angle is from this, it's 115 degrees. 115 degrees, and this is 0.6 on this guy here. So basically what I'm trying to tell you is you need to get your calculator to do this, because converting to rectangular format and doing this algebra, even for just a simple problem like this, is too much. It's good to go through this to see how this works out, but your calculator should be able to do this in polar format. So let's see, the only other thing I could probably do is I could make this guy look a little, I could redraw it. That's fine. I was going to draw the triangles, like I was going to draw let's see, it'd be something like this thing divided by this thing gives you this thing. You know, if you like that, do it. Anyway, part D, we have the phasor I, so we can just go straight to time domain. It's 0.6 cosine 4000 t. It's the same frequency. All the signals are going to have the same frequency in steady state sinusoidal. And then our angle is 115 degrees. This is amps. That's I of t. It's good to graph these things. So let's say let's graph V and I on here on t. So we've got V of t, which has a 25 degree phase angle and an amplitude of 30. So it's if you go back 25 degrees, this thing will peak. Okay, and this is the V signal, and then the I signal. If you go back 115 degrees, from here to here is 115 degrees. This I signal will peak. So this distance here is 90 degrees because 115 minus 25 is 90. And what that says is from peak to peak here, that I leads V by 90 degrees, which is exactly what you'd expect for a capacitive circuit. If it's purely capacitive, the current leads the voltage by 90 degrees. If it's purely capacitive. All right, that's just frequency domain and playing with, we're starting with time domain and we're going to frequency domain and playing with some phasors and then going back to time domain. Okay, start with time, go to phasors, go back to time.